So in this presentation today, we are going to talk about RAG, Retrieval-Augmented Generation. So we are going to talk about what is RAG, how you set it up, what are the components, what are the technical terms we use when we are building a RAG. We will explain all of that. And in the end, we will talk about Agentic RAG also. So to understand RAG, let's start with this very simple example where I have a chatbot which we all use. Today you go to OpenAI or Perplexity, you go and type your question in this chatbot and it goes to LLM, and this LLM is a large language model which is trained on the whole of internet information. And using that information, LLM answers the query and which is written back to the chatbot. So this is how a simple plain vanilla chatbot works, which is using the whole internet information as the information repository, and it knows everything. You ask anything, it will be able to answer. So much so, when it even actually really doesn't know, it will give you some answer. And that's what we call hallucination. And it will tell you with so much confidence, and the response will be so professionally sounding that most probably most of the people will believe LLM that it's telling the truth. Because 90% or 95% of the time, LLM does tell you the right answer. But 5% of time, it does tell you which is wrong or the information not existing even. But it tells you very confidently. So for that, we need something else. So let's look at this example, a very, very simple example, before we get into the real example of all the components of RAG. So suppose you want to build a medical agent, and you want this agent to respond only from these medical books, which you want to feed it to LLM. And it should not take all the information what it knows from the internet. It's a very specific agent you are building for helping doctors, for example, right? Or this agent can be anything else. It can be a human resources agent in your company which is telling the user about your HR policies. So there can be many examples of this specific custom agents where you want them to respond only using the knowledge base or the repository which we have provided to LLM. So that's where the RAG thing comes. So RAG is Retrieval Augmented Generation. So now we will look at all these three pieces separately. So on a very high level, how RAG works is, we take this data and we chunk and embed. We will talk about what is chunking and embedding in a minute. And then we put it in a vector database. And then when we build a chatbot, this chatbot take our query, embed it in the same manner, and goes back to this vector database and do a similarity search and get the data back from the vector database. And then it gives all of this to the LLM. And then LLM properly reformat the answer because now it has the query and it has the context also, and return back to the chatbot. So this is an example of RAG. Now there are many pieces here. So let's talk about one at a time. So the first stage of RAG pipeline involves bringing the raw document and data sources. And this is a foundational step, and it is very crucial for ensuring high quality input for subsequent stages. And this data can be anything. It can come from your database, or it can come from a book or some your proprietary documents. So in this stage also we do clean and prepare the data for vector database. This is the step where AI compliance come in picture. This is the stage where we clean the data. We make sure that we are not using any copyrighted data and the data is trustworthy and data is from proper sources. And here you don't want the data which is not compliant with your company policy. So this is the place you remove all the error from the data. A lot of the time it happens that this data has a lot of URLs pointer to some different information. So this may happen that you would like to pre-process this data and call all those URL and get the text and data from those URL to put in this data repository. Because when you are searching the vector database, you want all the data should be there ready for the consumption to LLM. So this step is very important where we are cleaning the data and maybe pre-processing. Sometimes you will pre-cook this data when I tell you that you go through the data and see if there's a lot of URL pointing to different document. Maybe you'll pull those data too in your data repository. So before we can put this data into the vector database, we have to do the chunking. So what is chunking actually? This is we take the whole text of say the whole book of 800 pages and we break that book into smaller chunks. So why we have to do that? So as you know, all language models, Claude, GPT-4 or any other model, they all have a maximum token limit, the context window. So here they have a limit. Today I believe OpenAI may have 2000 token limit and Google model they have I believe 2 million token limit. So this token limit is changing continuously, but still there's a token limit. And if a document exceeds that limit, you can't feed it directly to the model in a single pass. So chunking ensures each piece of text is within the allowable token size. So that's why we need chunking. And then it helps you in efficient retrieval too. In a RAG pipeline, a search engine or a vector database look for the most relevant text segment to a user query. And having smaller chunks make retrieval more granular and often more accurate. You can retrieve only the relevant part of a large document rather than the entire document. So you don't have to pull the whole 800 pages of the book. You just get the relevant information. And converting text into embedding and storing them in a vector database is more manageable when dealing with small chunks. So that's another reason you have to make that small chunk. And we'll talk in a minute about embedding, what is embedding. And this is all to improve the performance during the similarity search because each chunk is a more semantically focused. So this is what you have to understand, that each chunk may be more semantically focused. Okay? And it does reduce the noise. And the large documents can contain multiple topics or sections. But by chunking, you can preserve topic coherence within the chunk. So leading to a cleaner embedding. So this can help ensure that irrelevant or unrelated part of the document don't interfere with the retrieval. So when we are chunking, we can chunk in a couple of ways. We can say each chunk should be 500 token or 100 character each. Sometimes you can chunk on a paragraph or section boundaries. So when you are doing the chunking in all the tools, you have this parameter where you can say, I want a fixed size token, or I want to have a paragraph or section boundaries. Sometimes you chunk overlap also slightly with each other. So if you have a chunk with, say, every chunk is 500 token, you might overlap by 50 token with the next chunk. So transition aren't abruptly cut off. So all those numbers are there. When you are chunking in the code, you can play with these different things to see which chunking will helping you getting a better quality answer. So let me show you how the chunking and embedding looks. So now take a look at what is tokenizer and what is embedding. Suppose I have this sentence, the cat is sleeping on the couch. As you can see, it shows there are 7 tokens and 32 characters. And here is a vector representation of this string. And we utilize advanced embedding models such as OpenAI, like I chose here what model I want to use to do the embedding, to convert text into vector representation, because computers understand the number and vectors, and that's how the neural network works. And that's the reason NVIDIA GPUs are so expensive and needed in this world, because using GPU we can manipulate these numbers, these vectors, very quickly. And that's why we take this string, convert them into the numbers. So this is what is called embedding. So what happens is, if two pieces of text have very similar meaning, their embedding end up being closer to each other in the vector space. So now imagine I will take a second sentence where I say a cat is napping on a sofa. So as you can see, these two strings are very different. So wordings are different, but their embedding can be very close in vector space because they express a similar idea, that a cat is resting on the furniture. So as I said, if two pieces of text have a similar meaning, their embedding end up being close to each other in the vector space. So the embedding, let us quickly find relevant document or passages in a knowledge base by comparing similarity score, which is called cosine similarity. This is another parameter in the function where you pass and tell what kind of similarity you need. So this search in vector database is based on the similarity, how near the intention and the meaning and the context of two words are, rather than just looking for exact keyword match. So I use the word semantic search a couple of times and similarity. So what exactly semantic search is? Semantic search is the process of finding information based on the meaning of the query than just the matching keyword. So traditional keyword based search, like many classical search engine we had, would look for literal matches of word or phrases, but the semantic search, on the other hand, it understands context and intent. So let's go back here. So as we can see in this diagram, so the embedding generated should effectively capture the underlying semantic meaning of the text. This ensures that the retrieval mechanism can find relevant information based on user query rather than just the literal string. So for example, if I say, what is the capital of France? And another sentence is, which city is the capital of France? Should ideally return the same relevant result, Paris. And here, as we can see, both the query and the corpus documents are transformed into embedding using the same embedding models. So when the user asks the query, we embed that also. And when we move the data to vector database, we embed the data with the same model. Now here for vector database, we have multiple options. There are too many vector databases are there. Some famous one is Pinecone, Chroma, Milvus. So now even many of our traditional databases can also accept the vector data. Like Neo4j was graph database, and now it can be a vector database also. So the next step is to index the generated embedding within the chosen vector database. So indexing enables quick and efficient access to the embedding during searches. And remember, we talked about the similarity searches, right? So there are multiple different algorithms are there for similarity search. And this is again one of the parameters when you are doing the search, you can use it. So to optimize the retrieval, we need to configure the similarity search parameters. And this setup impact how the vectors are compared and how relevant results are determined. So in the context of text embedding, a similarity score indicates how closely two vectors representing pieces of text resemble each other in the meaning or context. So a higher similarity score generally suggests that the piece of text share more semantic overlap. So there are many kind of similarities are there. Cosine similarity, dot product, Euclidean distance, Manhattan distance, Jacquard similarity. It can be a complete separate presentation if you want to go deep into each kind of similarity, but just understand this is all taking this math vector and figuring out if I'm using the cosine similarity, how the math will work. And cosine similarity is the most popular for text embedding because it captures the angle-based similarity and it is less affected by vector magnitude. So two vectors magnitude can be different, but if their angle is less, they are more near to each other. For example, if you had mango and apple, both are fruit and they both will be near to each other in cosine similarity. So now we see till here we created the vector database and we created this chunking and embedding. So far what we have seen, we took the data and we chunk it, did the embedding and put it in vector database and created the index. Now we will start querying this database. So when users submit the query, we embed that same query with same algorithm and then look for data in the vector database. So for example, I searched some information and vector database return say 10 documents. Now we take this 10 document and give it to LLM with the query, with the new prompt. We may change the prompt for the context. And then LLM will take all this, the query and the information, and then it will return the data to the chatbot. So this is what RAG is. Now a couple of other things. Most of the time I've seen in Azure or in AWS, when you are searching this vector database, they just retrieve top K pages, top N number of pages. So there in Azure you can set it up for give me top 20 pages. And in Amazon also I think they have a similar limit, top 20 or 40 maybe, or maybe less than that. So why we have top 10 or top 20 pages? Because again, remember there's a context window limitation is there in LLM. So you cannot take all 800 pages and shove it into the LLM. Now because of this limitation, this RAG solution may not be right fit for certain kind of queries. For example, if you have this 800 pages book and you ask, give me all the keywords from this book, right? That will not be a right query for this RAG-based solution because it's not going to search all the pages looking for the keywords or saying, give me all the pages where the word, say, Microsoft is referred or any other keyword, right? So this RAG search will not search every page for you. It's looking at the similarity search. So yeah, I will not say it a shortcoming of RAG-based solution, but these are the limitations. So you have to understand when you are using this RAG solutions, what kind of query you can do and what kind of query is not right for the RAG solution. And there what you can do is you can change your prompt or you can think differently to get your answer. So as I said, it's a great solution for a lot of things, but it may not be the best fit for everything. This is, as we understand, this is the way the whole world is today using this RAG-based solution. So most of the solutions are based on this kind of architecture. But now we can look at, I'm calling it RAG++, which is Agentic RAG, right? This is a new term is coming in the industry. So what we are doing here, as we know, we've seen there are some limitations are there in the RAG, so how we can make it more comprehensive so it should be able to answer all my queries. For example, I still want a keyword search. I want to say, give me all the keywords found in this book, or I'm looking for a certain keyword. So it should just go and search the whole book. So what's happening for that, what we are going to do is we're going to put a LLM in front of the query. So what it will do, it will break the user query and say, okay, you want to do a keyword search? I'm going to call this different tool which is just does the keyword search for you. It can go there. Some query may need to go and refer some graph database. You can do that too. So here I'm showing data is coming only in vector database, but the same data, or it can be similar data, can go to graph database also. And as I said, even graph database support today the vectors. So you can have the similar kind of similarity matching in graph database also. And as you know, the graph database can be very good for certain scenario because they have a graph and then they have edges and then other nodes. So all this relationship is very well defined in a graph database. So that can be used as another source to create your final response. You have seen many times when you are talking to, say, OpenAI chatbot and you say, give a calculator question like multiply 2 by 3. That's not an LLM question as such, but that's a question for a calculator. And behind the scene, this LLM understand, okay, I need to call a calculator tool, so it will go and call this calculator tool, right? So you can build multiple different kind of tools for your scenario. And this first LLM can break your query, call different sources, call different tools, and then send all that answer with all the context and the query. So this LLM can build a final response for the user. And I'm showing here another thing, which is this LLM is calling this LLM back because it may realize the question is not good enough, or I want more information, or things like that. So this can go back to LLM, or it can go back to chatbot saying, I need more information. Like tell me, somebody, suppose this LLM or this chatbot is a very specific chatbot for your HR department, and you want to ask this chatbot, how many days of vacation left for me? Now this LLM can understand this question. It can call the tool to go and look at your vacation database, but it may decide, before I tell you about your vacation, I want to know who you are. So this LLM can go back and ask a question. Tell me your name. Tell me your employee ID, things like that. So that is what Agentic RAG is there, where you have inserted these smart agents, which are of course LLM based, but they can break the query, they can understand the query, they can summarize, they can ask more questions, and that's how you will build a Agentic RAG. And this is a very, very powerful tool. A lot of people are building the chatbot on their document repository. So you don't have to go and search your 5,000 documents looking for an information. You can just talk to your document repository and say, I'm looking for something, and the chatbot goes, searches the vector database and get you the response. Okay. So this is it. Now you understand what is RAG, Retrieval-Augmented Generation Systems. So thank you for your time, and let your feedback keep coming and let me know what else you would like to see on this channel. Thank you.